Okay, welcome back Mathcounts friends. In today's video we are going to be taking a look at problems 21 through 30 in the 2025 state sprint round. So this is part 2. I already made a video part 1 on the first 20 problems, and this will be the last 10 problems, which are the hardest ones. So let's jump right into it. This is problem 21. It says a convex quadrilateral ABCD has perpendicular diagonals. If AB is 5, DA is 11, CD is 12, what is BC? Okay, and it says express your answer in simplest radical form. Okay, so maybe what I'll do is I'll just redraw this over here. So I'm going to draw it going this way. So we've got 5 and 11 there. And then we've got the one that we want to know here, and 12 going this way. One thing is that you'll notice with this problem is that there seems to maybe be some missing information. So if this is 5 and this is 11, they don't tell you anything about this height. And so while that might be annoying in some ways, it can also be helpful because you can assume that it's going to be the same no matter what you choose for this height, that this x will be the same regardless of what that height is, which is actually kind of useful information. In fact, if you want, you can set that height all the way to 0 because it's got to be true regardless of what that height is. And if you set it all the way to 0, you just have a length of 5 plus 11 going across here, which is a total of 16. And then, from that we can figure out what x is. By using the Pythagorean theorem on these two right triangles. And it turns out if you don't make that assumption, if you don't say the height is equal to 0, it's kind of almost the same. It's just a little bit trickier, but maybe I'll do it that way just to be complete. So let's say this height of this triangle is big H, this height of this triangle is little h. So we can use the Pythagorean theorem. Well, I guess we should name these two. I don't know. Let's call this one A. Let's call this one B. So what we end up with if we do the Pythagorean theorem on all four of these triangles is we have a squared plus h squared equals 5 squared, and b squared plus h squared equals 11 squared. And then we have a squared plus big H squared. Maybe I shouldn't have used the same letter, but I've got an uppercase H squared is equal to x squared. And then big A squared plus B, not big A, I'm sorry, B squared. Oops. There we go. We got B squared plus big H squared equals 12 squared. Okay, so yeah, so basically what we can do is we can compute the difference between a squared and b squared from these two formulas. Okay, because if we subtract these two formulas, the little h squared will cancel out, and you've got well, I guess the best way to do it maybe is to just add these, or subtract these two formulas. You get a squared minus b. Is that going to be the best way to do it? Well, we'll see how it goes. We got a squared minus b squared equals 5 squared minus 11 squared. And then if you subtract these two formulas, you've got a squared minus b squared equals x squared minus 12 squared. So yeah, that works great because this a squared minus b squared is the same, so we can just set this side here equal to this side here and solve things, and that works out really well. So if we solve for x squared on one side, we get 5 squared minus 11 squared plus 12 squared. 5 squared minus 11 squared plus 12 squared. And then it's just a matter of figuring out what that is. So you got 144 here minus 121, right? So 144 minus 121, that's going to give you 23. And then you've got 25 here. So 25 and 23 is going to give you 48. So x is going to be the square root of 48. We can pull out, I guess we can pull out 4 from that. That'll be 4 times the square root of 3. So that is our final answer on problem 21. Let's move on to problem 22. This says let n be a positive integer less than or equal to 1,000. If the last 2 digits of n are reversed, the resulting integer is exactly 85% of n. What is the sum of the possible values of n? Okay, so we know it's going to be, well, since it's less than 1,000, it can have no more than 3 digits. So we can write it as the first digit. Let's call the first digit a times 100 plus b times 10 plus c is going to equal our first number, with a, b, and c being the 3 digits. And then if I reverse the last 2 digits, I'll get a times 100 plus c times 10 plus b. And those are not equal. I shouldn't have written the equal sign there. This one is, let's see, this one is, the last 2 digits are reversed, the resulting integer is exactly 85% of n. Okay, so that means I have to multiply this by 17 over 20, which is 85%, in order to be equal to this one. Okay, so let's multiply both sides by 20, and then let's subtract these two. So I'll have 17 times a times 100. This was supposed to be a plus here. My apologies. Plus b times 10 plus c. That's equal to 20. Whoops. 20 times 100a. I don't know why I'm writing a times 100. 100a plus 10c plus b. All right. Now let's subtract. Maybe we'll subtract this side from that side to give us 0 on this side. 0 is equal to, so we've got 2000a minus 1700a. That's going to be 300a. And then I've got 200c minus 17c. So that's going to be 283 times c. And then what have I got for b? Let's see, did I do that right? 200c. Yeah, I've got 20b minus 170. So that's going to be minus 150b. It's got to be equal to 0. Now, the first thing you might notice is that this 283c, well, the 300a minus the 150b, if we just look at that part, it'll have to be a multiple of 150. And so that means this other part here also has to be some multiple of 150 in order to add together to give you 0. And the only way, with a digit 0 through 9 for c, the only way to get this to be a multiple of 150 is to have c equals 0. So what that means is that our 3-digit number, well, okay, do we know it's a 3-digit number? I guess a could also be 0 maybe, so maybe we shouldn't jump to conclusions yet. But the c digit apparently has to be 0, and that's our ones digit. So yeah, I think the whole thing is going to have to be a 3-digit number, because if you had a 2-digit number and the lowest 2-digit number is 10, and when you reverse digits it becomes 1, and yeah, it's always going to be a lot less than 85%. So it's going to be a 3-digit number, and the last digit is going to be a 0. So we can ignore this part. That's just 0. And now we've got 300a is equal to 150b. That means the second digit has got to be twice as big as the first digit. So for example, 120 would be a possibility. Also 240 and 360 and 480. So those are all the possibilities where you have the first digit half as big as the second digit. And then the problem says, what is the sum of the possible values of n? So these are all the possible values of n. We just have to add them up. Of course, the 1 plus 2 plus 3 plus 4 gives us 10. And then this is double that. So we're going to have 1,000 from the summing up the hundreds and 200 from summing up the tens place. So that's going to give us a total of 1,200. All right, let's take a look at problem 23. It says, in how many distinguishable ways can two identical red marbles, two identical green marbles, and two identical blue marbles be distributed among four labeled urns, A, B, C, and D? Okay, so we've got these four urns called A, B, C, and D. And we've got two red marbles. We've got two identical green marbles, and then we've got two identical blue marbles. And wants to know how many ways we can distribute them among these four urns. It also says each marble must be placed in an urn. Okay, so you can't just leave one out. And no urn can contain more than one marble of each color. And then it also says up to two urns may remain empty. So you can't have 3 or 4 urns empty. But we already know that you can't have 3 or 4 urns empty just by the fact that the two marbles of any color have to be placed into different urns. As soon as you even place the two red marbles in, you're going to have only 2 empty urns. And by placing the green and the blue in, you're certainly not going to get more empty urns. So this last phrase is, you can just ignore it. It's kind of just extraneous information at this point. So the way to think about this is, how many ways are there to distribute the reds?
Yeah.
How many ways are there to distribute the greens? And how many ways are there to distribute the blues? So because you can't put the two reds in the same one, basically you're just choosing 2 of these 4 urns to place these 2 marbles into. So that's 4 choose 2, which is equal to 4 times 3 over 2, or 6. And the same thing is true with the greens, and the same thing is true with the blues. So you've just got 6 cubed. 4 choose 2, so it's 4 choose 2 times 4 choose 2 times 4 choose 2, which is 6 times 6 times 6, which is 216. So the answer here is 216. All right, let's take a look at problem 24. How many odd positive integers with at most 4 digits contain at least 2 even digits? Okay, so let's maybe start with, well, let's break it up by the number of digits. So first of all, it says we have at least 2 even digits, so we have to have at least 2 digits. And then it also says it's an odd integer, so that means the last digit has to be odd. So we have at least 3 digits. And if we do have 3 digits, it'll be even for the first digit, even for the second digit, and odd for the third digit. So that's one possibility. Another possibility is that we have 4 digits. And in that case, we've got a few different possibilities. We could have even, even, odd, odd. That would work. We could have even, 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 odd. Or we could have even, odd, even, odd. Or we could have odd, even, even, odd. We always have to have odd for the last digit because we know that the digit or the number itself is an odd integer. So these are our 5 possibilities, and I think we can probably combine these two together because the only difference is the first digit on those two. So we can just maybe instead of having those as 2 separate cases. Okay, so I can replace this even with, and then I'll just replace this whole thing down here. And then instead of having even and odd separate like that, I'm just going to say that this can be anything. I'll just put an X for anything. Okay, so the last digit, how many possibilities are there for what that last digit can be? Well, maybe let's take these one at a time, each of these 4. So the first digit here is even, but it can't be a 0 because that wouldn't be a 3-digit integer. So there are 4 possibilities for that first digit. And then the second digit has got to be even, so there are 5 possibilities there because that one can be 0. And then the third digit has got to be odd, so there are 5 possibilities there. So altogether that's going to give us 100 possibilities for that one. For the second one, we've got even, even, odd, odd. So the first digit, there are 5 possibilities. No, there are only 4 possibilities. My apologies, because you can't start with a 0 again. So 4 possibilities, and then the second digit, there are 5 possibilities. And then the third digit, there are 5 possibilities, and the fourth digit, there are 5 possibilities. Okay, so that's 125. Let's see, 125 times 4, right? So that's going to be, let's see, 500. 500 there, if I did that right. And then this next one, you have any digit for the first digit, except it can't be a 0. So there are 9 possibilities there. And then we've got 5, 5, and 5. So again, we've got that 125, 5 cubed here. So let's see. What is that? 125 times 9. Let's see, that should be 900 plus 225, 1125, I guess. And then here we have even, odd, even, odd. So the first even, again, cannot be 0. So we've only got 4 possibilities there. And then, okay, then we've got 5 possibilities for the second digit, another 5 possibilities, and another 5 possibilities. So, oh, let's see. I guess that's going to be another 500, right? Yeah. Okay, so all together we just add these all up, right? So we've got, this is 1,000, another 1125 is going to be 2125, and then this one is 2225. So that's our final answer for this one. Let's move on to 25. 10 fair coins are flipped simultaneously. What is the probability that the product of the number of coins landing heads and the number landing tails is at least 20? Express your answer as a common fraction. So we can have any number of heads from 0, 1, 2, all the way up to 10. And that's the number of heads. And the number of tails will be 10 minus that. So if we have 0 heads, we'll have 10 tails. 1 head will give 9 tails. 2 will give 8, all the way to 10 heads giving 0. And what we need to figure out is which ones of these possibilities multiply to give you something that's at least 20. So you can just multiply these pairs. You get 0, 9, 16. You can see we're going up. We're going to go up and then come back down to 0. So we got 3 and 7. That'll give us 21. Okay, so that's that. Everything but the first 3 and the last 3 are going to be at least 20. So what is the probability that the product of the numbers hit? Okay, so these are the ones we want to keep, I guess, right? The problem is that these are the ones that are hardest to figure out, because how many ways are there to get all tails? That's just 1 out of 2 to the 10th, so 1 out of 1024, right? And the same thing with 10 heads and 0 tails. That's going to be 1 out of 1024. But as you get to these ones in the middle, which are the ones we want, it's going to get harder and harder to figure out how many ways you can get that. Because we got to do 10 choose 3, 10 choose 4, 10 choose 5. Those ones are a little bit harder. So what we're going to do instead is we're just going to figure out the probability of getting 0, 1, or 2 heads, and then we'll multiply that by 2 to represent getting 8, 9, or 10 heads, since it's symmetric, and then we'll do 1 minus that probability to get the part that we want. So the probability of getting 0 heads is 1 out of 1024, and then the probability of getting 1 head, that's going to be 10 out of 1024, because that's 10 choose 1, and then 10 choose 2 is 45. So we have 45 over 1024 ways to get 2 heads. And if we add these all up, let's see, I'm not going to put a box around it. If we add these all up, we get 56 out of 1024. 56 out of 1024. Maybe we can simplify that a little bit even before we multiply by 2. So that'll be 23 out of 512. And then we multiply by 2 to include these other 3 possibilities. That'll be 23 out of 256. And then finally we need to take 1 minus that, right? Okay, resist the urge to put a box around it. So we need to do 1 minus 23 over 256. So that's going to be, I'll just use this little space here. So that's going to be 256 over 256. That's 1 minus 23 over 256. Right? So that's going to be, let's see, 233. Let's see, did I do this right? 55, 56, 56, 23, yeah, so 23 out of 512. So 233 over 256. I don't think I did that quite right. Oh, I messed up. This is not 23. This is 28. I'm sorry. This is 28. And that makes this 28 over 256. So we're subtracting 28 here. And let me fix this. So now instead of 233 over 256, what do we have? So we have 228. Is that right? 228 over 256. And that's divisible by 4 on top and bottom. So that's going to give us, let's see, 50 plus 7 is 57 on the numerator, and then 64 on the denominator. Okay, sorry for my mistake on that one, but the answer is 57 over 64. All right, let's jump to number 26. This is a tricky thing here. We've got like an embedded square root where there's a square root under the square root. And the trick to figuring out what this is to say, well, it's got some form like square root of a plus square root of b. Plus or minus, I guess, plus or minus square root of b. So what we say is that the square root of 7 plus 4 root 3 is equal to this, which means that this thing squared is going to equal 7 plus 4 root 3. All right, so what do we get when we, so we don't know what a is and we don't know what b is, but by expanding this out and matching up the terms, maybe we can figure out what a and b are. So we expand this out, we get a, square root of a times square root of a is just a, and square root of, whether this is plus or minus square root of b, we're going to get plus b, and then we're going to get plus or minus 2 times the square root of ab. And that's got to be equal to 7, well, there's a plus and minus here, plus or minus 4 times the square root of 3. So a times b has got to be 3, or I should say, actually, a times, no, because this is 4 here. So that means a times b has got to be 4 times 3. So a times b has got to be 12, actually. And then a plus b has got to be 7. So this thing's got to be 7. So what do we got? We got 3 and 4, right? So 3 and 4. If we say a equals 3, well, no. If we say a equals 3 and b equals 4, that's not going to be so good, because if we have square root of 3 minus square root of 4, that'll be a negative number. And the square root is definitely not a negative number. So we need to have a be larger. So let's go back. Instead let's have a equal 4 and b equal 3. And then we can plug this in. So we've got square root of 4 plus square root of 3. That's going to give us 7, if we square it, that's going to give us 7 plus 4 square root of 3. And if we have square root of 4 minus square root of 3, so let me just write this out. This thing squared is going to give us 7 plus 4 root 3. And this one squared is going to give us 7 minus 4 square root 3. So what we want is to take the square root of this thing, which is 4 plus square root of 3, and subtract the square root of this thing, which is 4 minus square root of 3. So we have square root 4 plus 3 minus, or sorry, plus square root of 3 minus the quantity square root of 4 minus square root of 3. And if you calculate this out, you just get 2 times the square root of 3. And the question said it's written in the form a square root of 3. What is the value of a? Okay, I probably shouldn't have used a here. That's a different a. But anyway, this is 2 times the square root of 3, so 2 is our answer here. Okay, let's take a look at this one. This one is problem 27. It's a tricky one. It says, in parallelogram ABCD, the 4 angle bisectors, okay, intersect to form another quadrilateral, which is, as you zoom in here, it's EFGH. And it says AB is 12, okay, and it says BC is, or no, Oh yeah, it says BC is 7, but since it's a parallelogram, I guess that means AD is also 7. And then it says, what is EG in centimeters? Okay, EG, that's this diagonal of this parallelogram here. Now, we had a problem earlier where I said there was kind of a gift of missing information. And there's a gift of missing information in this one too, which is that there's a flexibility in how you choose this angle here. They didn't say anything about that angle, and a parallelogram is flexible. I mean, you can keep these side lengths all the same, and you can change that angle down to as small as you want. And so this, if they're asking what EG is in centimeters, it must not depend on what that angle is. So we can use a little trick here and look at what the limit is as this angle goes to 0. So let's just imagine that we have DC across here, which is 12, and then we have a very small angle here. Maybe I should use my straight line tool here. So we have a very slight angle here, which is 7. And then we have another very slight angle up here, which is 7. And then we have our 12 across the top here, right? So, all right, so we have our 12 here, and our 7 here, and our 7 here. Maybe I'll just draw these points so they don't get lost, although that's not a very good color. But if you think about where the bisectors are, whoops, let's see if I can do this. So the bisector here is going to be very, very, it's going to be way down in there like that. And the bisector here is also going to be way down in there like that. And then there will be some bisectors of this angle, which will be almost vertical, going up like this. And so then our EFGH is going to be this little shape, this little quadrilateral in here. And what you can think about is, as you take the limit, as this angle gets smaller and smaller, this distance, EG, is just going to be, well, let's draw where that distance is here. So that's the distance from this point here to this point here. And what happens is, as you go down to a 0 angle here, this just becomes a vertical thing here, and that point E is just 7. I mean, it basically just becomes a line, right? And you've got point D here, and point A and E become the same. So A and E are both the same. They're 7 away from D. And then there's another 12. Well, there's another 7. I should say another 7 here. And then there's 5 in between because there's 12 across there. And so A and E are going to be there. And G, well, it's A and E and H, actually. And then this point will be C and F and G. C and F and G. And so they want to know the distance from E to G. That's just the distance from this point to this point. And that is just 5. 12 minus 7. So 5 is our answer here. All right, let's take a look at problem 28. This one says, what fraction of the permutations of the 10 letters in the word Mathcounts contains a substring of 8 consecutive letters that are all different? Okay, so we've got these 10 spots for where we can put these 10 letters. And we want to make sure that there is, let's see, how many have I got there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's put one more over here. We want to make sure that there's a substring of 8 consecutive letters that are all different. So are there any letters that are the same? Yeah, there's 2 T's, right? There's a T here and there's a T here. And there aren't any others that are the same. So the question is really all about where the T's are. If you put a T in the middle somewhere, there will not be a substring of 8 consecutive letters, right? If I put a T here, then I can only have, well, actually no, that's not true. If I have a T here, as long as the other T is way over here, or over here, one of those two, I can have a string that's 8 long, and it's all unique, right? So what's going to prevent me from having that string 8 long? Well, it turns out you have to put both T's somewhere in the middle. So let's say you put both T's in this region here. So if I put both t's in here, then that is exactly the ones where I won't have this substring of 8 consecutive letters. Because every substring of 8 consecutive letters, whether you start at the beginning or whether you go all the way to the end, you will always contain this region. And so if both t's are in there, then you won't have 8 consecutive letters that are all different. So maybe it'd be easier to figure out how many, what fraction of the time both t's are in this middle region, and then do 1 minus that at the end. Okay, so let's take a stab at that. So how am I going to figure out how many ways there are to stick both t's in this region and then have the others filled in? So basically what you need to do is you need to say, okay, how many spots are there here? There are 6 spots here. So I need to choose 2 of those spots to have t's. So how many ways is there to do that? There's 6, choose 2. And then once I choose those, once I do the 6, choose 2, then I have 2 t's. They might be here and here, for example. And then I've got 8 spots left, and I can permute the other letters however I want. So I do 6, choose 2 times 8 factorial. That should be the number of ways that don't have the substring of 8 consecutive letters. And then I can divide by the total number of ways to permute the letters, which is not just 10 factorial because there are 2 t's that are the same. So it's really 10 factorial divided by 2. 10 factorial divided by 2. Okay, so maybe I'll take this 2 and put it up on top. That way we don't have a denominator under the denominators. How's that? So we'll just do 10 factorial there, and we'll put the 2 up on top. Okay. So let's take a look at what we have. We're almost there, I think. So now we just need to compute this, and then we need to do 1 minus this as well. So 6, choose 2, that's 6 times 5 divided by 2, that's going to be 15. This is equal to 15 times 8 factorial times 2 divided by 10 factorial, right? So I can cancel out most of the 10 factorial with this 8 factorial. And then what I have left is 8 times 9, or 90. And then this 15 times 2 gives me 30, right? So this is 30. And so I have 30 over 90. This is all equal to 1/3. And so I just have to remember now to do 1 minus this to get my answer, because this 1/3 is the fraction that doesn't have the consecutive letters. And so I do 1 minus this to get the fraction that does. And so that'll be 2/3. So now I'm going to really circle that one. That's our final answer. Okay, let's go ahead and move on to problem 29. This one says, let S be the sum of all positive integers that are factors of 9999999. What is the largest prime number that is a factor of S? Okay, so one thing that I think is helpful here is if you happen to recognize that 9999 is actually 1001 times 999, right? Because the 1 part times 999 gives you the last 3 digits, and the 1000 part times 999 gives you the first 3 digits. So that's already useful. We basically need to find the prime factorization of this. So we can break this up into 999 and 1001. Now 1000, let's see, 999 is divisible by 9, right? That's going to be 9 and 111. 111 is divisible by 3. Let's see, so that's going to be, let's see, 30, it's going to be 40, no, not 40, 37, 37. And then, okay, so now 9 is going to be 3 squared. And then 1001, what is this divisible by? Well, it's divisible by 11. If you know your divisibility rules, the odd digits add up to 1 and the even digits add up to 1. So this is divisible by 11. And what is that going to be? Let's see, 1001. If I divide that by 11, let's see, this goes in like 9 times. Oh yeah, it's just going to be 91, right? So 11 times 91. So now do I have the prime factorization? Let's see, 91 is 91 prime. 91 is divisible by 7, I think, right? Yeah, because that's going to be 13 times 7 is 91. Oh, that's a tricky one. Okay, so this is actually 7 times 13. Okay, so I think I have the prime factorization now. So let's write it all out. I had 3 3's, so that's 3 cubed, times 37, times 11, times 7, times 13. Did I get everything? I've got my 13, I got my 7, I got my 11, I got my 37, my 3 3's. Yeah, so this is a prime factorization of 999,999. Now it says, what is the largest prime number that is a factor of s, which is the sum of all the factors? So how do we compute the sum of all the factors? Well, there's a trick for that. If you know the prime factorization, there's a way to compute the sum of all the factors. And the way you do it is you take each one of the prime factors. So, and then you do this. You do that factor to the 0 plus that factor to the 1. Well, all the way up to the factor to the power that it is in there. So it's 1 plus 3 plus 9 plus 27. That's the sum of all the factors that just have 3. And then you multiply that by 1 plus 37 for this part. Since the exponent here is 1, we just have to go to 0 plus 1. And then you multiply that by 1 plus 11. And then you multiply that by 1 plus 7. And then you multiply that by 1 plus 13. So this number here, when we multiply this all together, that will be the sum of all the factors of 999,999. And so this, we can just find the prime factorization of this product and look for the biggest prime among those. So let's see. This one's going to be 14, so its biggest prime factor is going to be 7. This one's going to have a bunch of 2's in it. This one's going to have a 3 and a 4. 38, let's see, 38 is going to be, let's see, 19 times 2, so that'll have a 19. That's our biggest prime factor so far. And then this part here, let's see, this will be 30, this will be 40. 40, the biggest prime factor, is going to be 5. So 19 is actually our biggest one. So 19 is the answer to this problem. Okay, we're on to the very last problem now. This is problem 30. It's a pretty tough one. It says if x and y are real numbers such that 4 minus x times 4 plus y equals 2, and 4 plus x times 4 minus y equals 3, what is the value of x squared minus 1 times y squared minus 1? And express your answer as a common fraction. So really the key here is to find all the right substitutions. One thing you can start with is factoring this out. This x squared minus 1 is x plus 1 times x minus 1, and then you've got y plus 1 times y minus 1. And we can combine some of these terms, opposite terms, like for example we can combine, maybe we should do a plus and a minus. So if we do this times this, we get xy minus x plus y minus 1. And then if we multiply these two together, we get xy, and then we get we get plus x minus y, and then minus 1. And so we're looking for this product here. And one thing I'd like to point out is if we can figure out what xy is, that will be helpful to compute this. And also if we can figure out what x minus y is, because this is x minus y and this is the negative of x minus y. So if we can compute those two things, we'll be well on our, we'll be there basically. So now if we look back up at these two given expressions up here, we might look for ways that we can compute xy and x minus y. All right, so let's just multiply this out. So we've got 4 times 4, we got 16 minus 4 times, let's see, this will be y minus x. Maybe I'll put plus x minus y. Or wait, which one is it? No, it's minus x, so sorry, it's minus x minus y. Let's do it. Yeah, minus 4 times x minus y. because that'll give us a negative x and a positive y. And then you've got minus xy equals 2. And then if we do the other one, we get something similar. It's 16 plus 4 times x minus y. Here's that x minus y that we're looking for, and the xy. And then you've got a minus xy here. And that's equal to 3. So we can add and subtract these two equations and see what it gives us. Let's start by adding these two equations. So that'll give us 32. All this stuff will cancel out. And then we'll have minus 2xy equals 5. Okay, so we can work things, subtract 5 and add 2xy. We get 27 equals negative 2xy. So that'll give us xy, I'm sorry, not negative, that's positive. So that means xy is equal to 27 halves. Okay, so that's one part that we were looking for. We wanted that to be able to figure this out over here. The other thing we're looking for is the x minus y. So now, instead of adding these two equations, let's subtract them. So maybe we can do a plus on this equation and a minus on this equation. The 16s, we'll put that in parentheses. The 16s will cancel. The xy's will also cancel. And we'll have, let's see, 8 times x minus y. 8 times x minus y on this side. And then that's going to be equal to 3 minus 2. That's just 1. So this is pretty simple. We just get x minus y is equal to 1/8. Okay, so now we have the two pieces that we were looking for. We can go back to here. And we can try to plug things in. So let's grab a different color. So this thing is going to be equal to, remember we had the product of these two because it was a product of all four of these. So the product of these two, we're going to have xy is 1/8. Or not, no, xy is not 1/8. xy was 27 halves. So we have 27 halves minus x plus y. This is that minus x plus y is the same thing as subtracting x minus y. Right, so x minus y is 1/8, so this is minus 1/8, and then minus 1. Okay, great. We can figure that out. And then the other one is 27 halves, again, 27 halves, plus x minus y, so that's plus 1/8, and then minus 1. Okay, great. So we just need to figure out what this is. Maybe let's put it all into eighths. So let's see, 27 times 4, that's going to give us 108. So we got 108 eighths minus 1. So that's 108 minus 1 over 8. Oh, but we also have to subtract this 1, so that's minus another 8. So this top one is all of this. And then the other one will be, let's see, 108 plus 1. So this is 108 plus 1 minus 8 over 8. So what is that? 108 minus 1 minus 8. That's going to be 99 over 8. 99 over 8. And then this one is going to be 101 over 8. 101 over 8. Okay, so we got this 101 times 99. That's kind of similar to what we had in that other problem with all those 9s. This is just going to be 9999. So we've got 9999 on the numerator, and we've got 64 on the denominator. And can't simplify that anymore because it's all 2's on the denominator, and this is odd on the top. So that's our final answer for problem 30. I hope you guys enjoyed this video, and I'll see you guys in the next one. I will be making a video on the target round as well. Take care, bye.